Hello students, in this class let us study spring block system. Let me consider a spring of spring constant K attached to a rigid support and the other end is having a mass M. K is the force constant or spring constant. In this case, the spring considered is massless compared to mass attached to its free end. If this body is in equilibrium and it is displaced by a small distance x, force, which is restoring force, is developed in the spring, which is equal to minus k times x. Since this force is directly proportional to the displacement and its direction is always opposite to the displacement, this system will perform simple harmonic with the frequency omega that is equal to square root of k by m, or time period of this system t is equal to 2 pi into root of m by k, where k is spring constant. And remember that the time period for spring mass system is independent of acceleration due to gravity. Therefore, for this system with any orientation, whether it is vertical, horizontal or inclined, time period depends only on the mass and spring constant. This spring constant K is dependent purely on the material and its geometry, and this K is inversely proportional to length of the spring. Say L is the length, then K is proportional to 1 over L, or you can write this as K into L is a constant, product of spring constant and its length. So shorter and shorter the spring, its spring constant is more, and for large values of L, its spring constant will be small. Now let us consider a spring mass system. Let me consider a spring having a mass small m attached to a mass capital M. This mass is capital M, mass of the spring is small m. The time period of this system is equal to 2 pi into root of mass of the block capital M plus mass of the spring divided by 3 whole divided by spring constant of this system capital K. Now consider a spring of total length L with the spring constant value K, and this is cut into two parts of length L1 and L2, and now the new spring will have a constant K1 and this spring constant will be K2. We know from this relationship that K is inversely proportional to L, or KL is constant. I can write KL equals K1 into L1. Since length is decreased, its spring constant value is increased. That is equal to K2 into L2. From this relationship, what I can write is L1 plus L2 is equal to initial length of the spring, that is L. So the value of spring constant K1 and K2 can be calculated. From this equation, I can write KL equals K1 L1, or K1 equals K into L divided by L1. This can also be written as K into L1 plus L2 divided by L1. Similarly, K2 is K into L1 plus L2 divided by L2. So the spring constant value of new part of the spring of length L2 is equal to K into L1 plus L2. If spring is cut into n equal parts, the spring of length L is cut into n equal parts, then force constant of each part is equal to, say, K prime, that is equal to n times K. Since we are decreasing the length, its value of K will be increased. And how many times? For n times, as all the parts are of same length. Next, if both the ends of a spring are connected to different masses m1 and m2 having a spring constant say k, then its time period t is equal to 2 pi into root of mu divided by k, where mu is reduced mass of the system, reduced mass, and that is given by mu is equal to product of the masses m1 into m2 over sum of the masses m1 plus m2. This is time period of a spring having blocks at both the free ends, both the ends. Now let us study how does value of spring constant vary for combination of the springs. Let me consider two springs connected in series with spring constant k1 and another spring of constant k2 attached to a mass m in series. So for this combination, what is the effective spring constant? Let k be the effective spring constant, then the value of k is equal to 1 over k is equal to 1 over k1 plus 1 over k2. If two springs of spring constant k1 and k2 are attached to a same mass m and they are showing time period t1 and t2, now both the springs are connected to the mass in series, then the time period of this combination is equal to say t series ts is equal to square root of t1 squared plus t2 squared. These are two separate springs connected to same mass in series. If they are connected separately, their time period is t1 and t2. Next, parallel combination of the springs. If two springs k1 and another spring having spring constant value k2 are attached to a mass m, then what is the effective spring constant for this combination? So in this case, both of the springs are undergoing compression or extension equally. Therefore I can write if the combination is displaced by a distance say x, then the force is F is equal to the effective spring constant k into x, and individually force due to this spring 1 is k1 into x and force due to this spring is k2 into x. So I can write this as F is equal to force of first spring and force due to second spring, and that is k1 into x plus k2 into x, and this is some effective spring constant into x. So from this killing x, I will get k is equal to k1 plus k2. Therefore, for parallel combination of the springs with spring constant k1 and k2, the effective spring constant value is sum of individual spring constant values. Now let us say T1 and T2 are time periods of individual springs connected to this mass M, and now they are connected to the same mass in parallel combination. Then the new time period for this combination is given by T parallel is equal to product of individual time periods T1 and T2 divided by square root of T1 squared plus T2 squared.